As you can see from the objective of this page, we're going to be looking at finding the antiderivative of a function. So the first thing that I'd like for you to do, if you are in my class, is to go to page 1 in your packet, and on the left hand side of page 1, as you can see from the screen, that is a warm-up. So the first thing I'd like for you to do, if you're in my class, is to stop the video, do the warm-up, which is the first, what do we have here, 4 or 5 problems finding the derivative. So at this point, stop the video, go back, find the derivative of those functions. So in problem number 1, when you find the derivative, that's pretty easy stuff. You get dy dx, or I could write y prime, is equal to 6x, and that's done by the power rule. Number 2, we have almost the same function. In problem number 1, we have a quadratic function of 3x squared plus 4, and number 2, we have a quadratic function of 3x squared minus 7. So notice that in these two, the base function 3x squared is the same, and then in the first function we have a plus 4, which transforms the parabola or shifts the parabola up 4 units vertically, and in number 2, the parabola is shifted down 7 units vertically. However, the derivative is going to be the same. The derivative on the left-hand side, the derivative of y, is dy dx, and the derivative on the right-hand side is 6x. So we have two functions that have the same derivative. They have the same slopes at the same values because, again, we pointed out that these two functions are simply transformations of each other's. So they belong to a family of functions. Notice that the two functions in this family share the same derivative. Okay. In problem number 3, we basically have kind of the parent of this family, although x squared would be the actual parent, but for this particular family, the derivative on the left-hand side of y is dy dx, and on the right-hand side, by the power rule, we get 6x again. So notice that we have these functions that belong to the same family, and something important to note is that all 3 of these functions have the same derivative because they're simply vertical translations of each other. Their shape is the same, therefore their slopes at the same x values are going to be equal. Moving on to problem number 4, on the left-hand side, the derivative of y is dy dx. And on the right-hand side, by the power rule, the derivative is 6x squared plus 4. In problem number 5, finding the derivative on the left-hand side, we get dy dx. And the derivative of sine, which is a transcendental function, is cosine. So what you've done there is old stuff, easy stuff, stuff you already know how to do. So how does that connect to what we're about to learn? Well, if you look at the right-hand side, the notes, the classwork, we're finding a function whose derivative is given. So we're going backwards. In mathematics, to undo addition, you subtract. To undo subtraction, you add. To undo multiplication, you divide. So in other words, pretty much for every operation you do in math, there's a way to go back. And that's what we're going to look at today, or in this particular lesson. We're going to look at how do you go back to the original function if you start with the derivative. Notice in the warm-up, we were given an original function, and in every case we were finding our slope generator. We were finding the derivative of the function. But now we are finding a function whose derivative is given. Now there is definitely a connection between the left-hand side and the right-hand side. So let's change colors here. First of all, if we're going to find a function whose derivative is given, again, I would suggest you stop the video, try to go through these and see if you can figure it out for yourself. But I'm going to go ahead and talk about it. We can see very clearly in the warm-up that there are 3 functions that have the same derivative. So if we were to go backwards, if we know that the derivative of our function is 6x, we can kind of cheat over to the left-hand side and say, well, then the original function is y equal to 3x squared. The question is, Is it 3x squared plus 4, like in the first example? Is it 3x squared minus 7, like in the second example? Or is it just 3x squared, technically, plus 0, like we have in the third example? And the truth is, we really don't know if there was a constant to this function. There might have been, there might not have been. So to take care of that, we're going to put a plus c. The c represents a constant that could be there. In this case, the constant could be, we don't have any way of knowing without being given more information, the constant could have been 0, the constant could have been 4, the constant could have been negative 7, the constant really could have been anything. In order to figure out what the constant is, if there really was a constant, we would have to know more about the function. So based on what we have so far, all we can say is that if we have a derivative of 6x, it would take us back to a family of functions. So here we go with that whole idea of a family again. A family of functions. Now if you go back over to the warm-up, remember the parent, so to speak, of this family was 3x squared, and 3x squared. The plus c means that we could vertically translate. So here is that vertical translation. That's all that this c value does, because it's a constant. It would be a vertical translation. And that's why we have an entire family that all share the same derivative. Now, the inverse of addition is subtraction. So we have symbols to indicate that we're going to reverse that operation. The question then would be, well, what's the symbol that indicates that I'm going to go backwards, or I'm going to start with the derivative and go back and find the original function? Well, we know the golden rule of equations is whatever you do to one side, you have to do to the other. So in number 2, even though you're looking at it thinking, well, isn't that the same problem? Absolutely it is. I now want to show you the symbol that indicates that we are going to go back. Remember, whatever you do to one side, you do to the other. Another thing that I want to do when I reverse the process, notice that on the left-hand side, I have my dy and my dx together. And notice on the other side, I have only a 6x. In other words, I don't have any x's on that side. And I want my function, I want y in terms of x. So the first thing I'm going to do to make that happen is I'm going to, if my eraser will come up, I'm going to get all of the y's on one side and all of the x's on the other. In other words, I'm going to multiply both sides by dx. And if I multiply both sides by dx, I'll get dy is equal to 6x dx. So I'm kind of taking the derivative apart. Now I have my y on the left-hand side and my x's on the right-hand side. Now to reverse, the symbol that indicates that I want to reverse the process is, it looks kind of like an S. It's an integration symbol. So it implies that we're going to integrate. And another way to think of integration is we're finding the antiderivative. In other words, we're going backwards. We have a derivative, antiderivative, we're going to go backwards, or integration. Those two terms are used fairly synonymously. Now notice let's start with the right-hand side. Everything is in terms of x. We're going to reverse that process. So if I didn't have my warm-up, how would I reverse the process? Well, I'm reversing the power rule. So let's think, what did I do when I'm using the power rule? So let's go back over here to example number 2, where I have 3x squared minus 7 equal to y. On this side, the power rule, normally we take the exponent, multiply, so we get 3 times 2 is 6, and we decrease the power by 1. So we get 2 minus 1, which is 1. The derivative of a constant is 0, so that's really not a big deal when we're finding the derivative. How do I undo that process? Well, to undo multiplication, I have to divide. To undo subtraction, I have to add. So let's go backwards. The power of x is 1, so I'm going to increase the power by 1, so I'll get 6x squared. Remember, we're reversing the process. And then instead of multiplying, I'm going to divide by the new power. So there's my 6x squared over 2. Remember, we said we don't know if there was a constant or not, so we're going to add a plus c in there. On the left-hand side, we're going to basically do the same thing. There's an understood 1. This is 1 dy, whereas on the right-hand side I have 6x dx. 1 dy. We're going to find the antiderivative, but on the left-hand side, everything is in terms of y. So if which function has a derivative of 1? In terms of y, when I go backwards, I bring the variable y back. So I get y equal to 6x squared over 2 plus c, which is the same thing as y equal to 3x squared plus c. So again, I'm indicating that I have a family of functions. The base of the family is 3x squared, and then all of the functions vary by a constant. The constant could be 0, constant could be anything. I don't know the constant without more information. Problem number 3, again, the same problem. So let's just, for posterity, go ahead and do the problem. We're going to separate our variables by multiplying both sides by dx. So I'll have dy equal to 6x dx. I need a symbol that says I'm going to reverse the process. I'm going to go from a derivative back to the original function. So I'm going to find the antiderivative, or the integral of both sides. There's an understood 1 on the left-hand side. So when I anti-differentiate or go backwards in terms of y, I'll get the y back. On the right-hand side, when I reverse the power rule, I'm going to increase the power by 1 and divide by the new power plus my constant. When I simplify, I get y equal to 3x squared plus c, which again gives me back to the original function. And we have a family of functions that share the same derivative. The family of functions differ by a constant. So let me just write that. This derivative generates a family of functions that differ by a constant. There are an infinite number of functions that have this same derivative. Problem number 4. We're going to reverse the process, so now we know what to do. We're going to multiply both sides by dx to get the x's on one side and the y's on the other. So I'll have dy is equal to 6x squared plus 4 dx. Now I'm going to find the antiderivative of both sides. One thing I haven't spoken to yet, let me give myself a little space here. Come on, eraser. There you go. Oh, I did it again. Sorry for the pause in the video. Okay, back to work. I'm going to find the antiderivative of both sides. One thing I have not spoken to yet is this whole idea of the dx and the integral. Basically, if you'll take a look at the symbol and the dy, they kind of work together as my operator. Think of it kind of like that. The integral and the dx on this side work together as the operator. It basically says I'm going to find the antiderivative. The dy tells me I am in terms of y. So on the left-hand side, the variables that I bring back are going to be y variables. The dx on the right-hand side tells me, well, this side will be in terms of x. And that's why I wanted to separate my variables, because I'm finding the antiderivative in terms of two different variables. So again, these two work in conjunction. They are the operator, and what I'm operating on is the inside function, and that function is always a derivative. It's someone's derivative. So if we reverse the process and find the antiderivative of 1 in terms of y, we bring the y back. On the right-hand side, we're going to reverse the power rule, so we're going to increase the power by 1, so we get 6x cubed, divide by the new power, over 3. The antiderivative of 4, which is a constant, we bring back the x. Now you can check these by finding the derivative. We'll talk about that in a second. And then there could have been a constant of integration. We have no way of knowing without more information. When we clean up the function, we get y is equal to 3x squared. Well, let's try that again. I guess I'm fixated on the last function. When I clean up, I get 2x cubed plus 4x plus c. Now earlier I said you can check that by finding the derivative and see if it takes you back to the given derivative. And if you use the power rule, you will get the original derivative, and you can see that it matches up to problem number 4. Problem number 5, we're going to separate the variables, so we get our dy equal to cosine of x dx. We're going to find the antiderivative of both sides. Whatever you do to one side of an equation, you do to the other. On the left-hand side, when you find the antiderivative in terms of y, remember there's an understood 1 there, you get y. On the right-hand side, here are my operators working together telling me I'm finding the antiderivative in terms of x. And this is, now you have to think about the derivatives of your trig functions. You have to think about them backwards. So you're thinking who or what has a derivative of cosine x. You have to think of it backwards. And that would be sine x. Don't forget your plus c, which is your constant of integration, because we're generating, I want to keep drilling home, a family of functions that share the same derivative but differ by a constant. And so my original function is y equals sine x plus c. All right, let's summarize what we've done here. The process of finding, this should be finding, an original function, so that is our objective. Find the original function. We're going to be given a derivative, is called antidifferentiation or indefinite integral. And I've mentioned that already in the discussion. The symbol that you see here, we already talked about the fact that if you find the antiderivative, we are in terms of x. This is what tells you the variable that you're working with. The function that you're operating on is someone's or some function's derivative. So we're finding the antiderivative of a derivative. When you find the antiderivative of little f, we're going to use little f to indicate derivative. It brings back big F, which is the original function, plus we already talked about c being a constant. And in some cases, we'll have a way to solve for that c if they give us enough information. The solution to this differential equation, I'm over here, the solution to this differential equation, and that's exactly, we start out with a differential equation. What the heck's a differential equation? It's an equation involving a derivative. In other words, it's pretty self-explanatory. So a differential equation would be like we had on the first page. dy dx is equal to 3x. That's a differential equation because it's an equation with a derivative. The solution to the differential equation, solution implies that we're going to find the antiderivative. So I want to take all these words apart for you. It generates a family of functions, there's that whole theme again, who share the same derivative. So what does the family have in common? They share the same derivative. The members of the family differ by a constant c, which we talked about being a vertical translation. So it's one function, all shifted up or down. All right, let's look at that visually. Same problem that we had earlier. We're going to find the antiderivative. Now notice this time we're not starting out with a differential equation. We're basically given the problem to find the antiderivative in terms of x of the function 6x. We're going to reverse the We're going to reverse the power rule. So we increase the power by 1, 6x squared, divide by the new power, plus a constant of integration. When we clean that up, we get 3x squared plus c. Then it says sketch a graph of the family of functions who share this derivative. Well, what I'm talking there is 3x squared plus c. Well, as we talked about earlier, c could be 0, c could be 1, c could be 2, c could be a half, c could be negative 3, 4. C could be anything. So the basic parent function, so to speak, would be 3x squared, which would look something like that. Then we might have 3x squared plus 4, or 3x squared plus 10, or we might have 3x squared minus 2. So this would be our family of functions that share the same derivative. I'm sure it's obvious to you that I did not draw these parabolas to scale, but they're supposed to be vertical translations of the function 3x squared. All right, so graphically speaking, that's what's happening. And if I had drawn these parabolas to scale, then if I selected the same point on every function, then the slope of the tangent lines, if I drew the tangent lines in there, they should be parallel to each other, because the slope on each function at that particular value of x is the same. Number 2, we're finding the antiderivative of 6. We are in terms of x. These two work together to tell me that I'm finding the antiderivative in terms of x. So I'm going to reverse the process. Who has a derivative of 6? That would be 6x plus my constant of integration. Don't forget the constant of integration when you're finding an antiderivative. Problem number 3 is a power function, so we're going to reverse the power rule. We're finding the antiderivative, and we are in terms of x. So we're going to increase the power by 1 and divide by the new power.
Good morning.
Then we're going to go to second term. We're going to increase the power by 1, divide by the new power. Who has a derivative of 1? That's x plus the constant of integration, which gives me 2x cubed minus 2x squared plus x plus c. Problem number 4. We're going to, before we start on this problem, we're going to need to do a little bit of algebra and rewrite the expression. So I'm going to change this into the antiderivative of 6x to the negative 2/3 power. So now I just use the power rule, finding the antiderivative in terms of x, increase the power by 1, so negative 2/3 plus 3/3 gives me 1/3. If I'm dividing by 1/3, that's the same thing as multiplying by 3. If I divide by 1/3, because remember you divide by the new power, that's the same thing as multiplying by 3, plus my constant. 3 times 6 is 18x to the 1/3 power plus c. That would be my original function. Problem number 5. I'm finding the antiderivative of secant x tangent x. That's what I call a who has derivative. You have to think backwards. Who has a derivative of secant x tangent x? Well, that would be tangent x. That's just a memorization thing, plus c. And how do you check yourself? You find the derivative. What's the derivative of tangent x? That's wrong. Wow. Let's try that again. And see, when I caught myself when I asked myself the question, what's the derivative of tangent? Well, the derivative of tangent x is secant squared x. So I knew I made a mistake. Who has an antiderivative, or who has a derivative of secant x tangent x? That would be secant x plus c. How do I check that? What's the derivative of secant x? Secant x tangent x. So be careful with those trig ones, because they can get very tricky and confusing. Number 6. The easiest way to view number 6 is to kind of take it apart and think of it as pull the 6 out in front as a coefficient 1 over x. Because when you see it like that, hopefully that starts to ring a bell. Who has a derivative of 1 over x? Well, that would be ln of the absolute value of x plus c. Because what's the derivative of ln of x? 1 over x. All right, lastly, we have a quotient. So like I did in number 4, I'm going to clean it up first, and I'm going to take that square root of x, which is x to the 1/2 power, and I'm going to take it into every term in the numerator. So I'll get 6x to the 1/2 power minus x. Now remember, 3 would be 6/2 power, so x to the 5/2 power plus x to the negative 1/2, and I'll try to squish my d. There's a dx behind that. Reversing the power rule, for each term, I'm going to increase the power by 1, so I get 6x. If I increase by 1, I'll add 2/2, which gives me 3/2. Dividing by 3/2 is multiplying by 2/3. Minus, increase the power by 1, so if I add 2/2 to 5/2, I get 7/2. Divide by 7/2 is to multiply by 2/7. Plus, increase the power by 1. Negative 1/2 plus 2/2 is 1/2. Divide by 1/2 is multiply by 2, and then my constant of integration. Last thing is to clean that up. So 3 divides into 6 twice. 2 times 2 is 4, so I get 4x to the 3/2 minus 2/7 x to the 7/2. Let's move this guy out of the way. Plus 2x to the 1/2 plus c. And that is the process of finding a general antiderivative. We'll talk more about particular solutions versus general solutions in class, but this is a good start to reversing the process of being given a derivative and then going back and finding the original function. Hope this helps you.